thanks very much for introducing me and for inviting me here. And thanks for all who are attending this contribution here. It is a little different with regard to the power to X, power to gas point, since I will explain this very briefly and soon. It is the direct way how to use solar light for solar fuels production. And first of all, I would like to thank the co-authors, in particular Agnieszka Pajuk, who does a lot of epitaxial growth and analysis of the interfaces. I will explain this later. And in the frame of a new project, which is the direct and efficient photoelectrochemical CO2 reduction, we have PhD students, David Ostheimer in particular, Manali Nandi, and of course, and very important, the collaborating sites, which is the California Institute of Technology Joint Center of Artificial Photosynthesis, Helmholtz-Zentrum Berlin, and Fraunhofer ISE, in particular Frank Dimroth, Harry Edwater, and Ulf van der Kroll at the different sites. I would like to thank a lot. They are all together with us dealing about this usage of tandem structures for efficient solar fuel production. And in addition, I would like to thank even more co-workers and for financial support by the Federal Ministry of Research and Education, Tokyo University, Professor Sugiyama, Academy of Science of Czech Republic, Alex Romaniuk, the company Space for a long-lasting cooperation in Munich, Technical University of Munich, Ian Sharp, and Rainer Eichberger, Klaus Schwarzburg. So it is necessary to have very complex and different cooperation, as I will explain in my talk, since we are challenging here many different problems. And the difference, just to explain this here again, with regard to the power to gas conversion, is that we are trying the direct way for photoelectrochemical solar fuels production, which does not need two different systems and is a kind of an artificial leaf. You can see this here on the right-hand side. We are splitting water here, as nature it does in a two-step process. In nature, in natural photosynthesis, it is called the set mechanism, so a two-step process. And here we are using a tandem by exploiting the light sufficiently. First, the high energy part, and secondly, the low energy part, having then the reactions of the water oxidation at the anode. You can see this here below. And afterward, at the cathode, the reduction of the hydrogen ions here at in this case, at the side of the device structure here where the light is impinging. So next, I would like to show that there is several advantages for this more challenging way how to use solar light for solar fuels production. As I told, we do not need two separate systems, just one system. We have a kind of an artificial leaf with no electric circuitry, no basic electric environment. We have basically the advantage to use lower current densities. So there's the idea that we can also use less precious catalysts. We have seen this already, the role of catalysts in the last talk. And in principle, this way is thermodynamically more favorable compared to using photovoltaics for electric power generation, and afterwards an electrolyzer. And beyond this, there is the opportunity also to produce in both ways, of course, different products as solar fuels. The simplest and easiest product is hydrogen, and beyond this we have more opportunities, for example, methane, formate, and so on. This you see here is energetically difficult to address, and there a high selectivity of the catalysts is necessary. Here we also work, as I already mentioned, in a project together with partners in Munich, Berlin, Arts for Space, and Fraunhofer ESE for the CO2 reduction. So first, I would just spend some educational remarks. What do we have to do? What do we need to do to efficiently produce solar fuels, in particular, in this case, hydrogen by water splitting? So as you can see here, the whole device of a tandem structure is really complex. We have many demands to do this efficiently. First of all, we have to have the solid liquid interfacial reactions, as you can see here. So this interfacial reactions should occur without having a lot of losses by non-radiative recombination. We have to make sure that we have a very good electronic alignment with the whole device, and within the whole device, and with the device and the support and the catalysts and the environment. This is also a real challenge. And we need to direct the charges at charge separating contacts, as you can see here, for separating electrons and holes in the tunnel junction. All this has to occur with a high efficiency. So there's different challenging and difficult parts in this device structure, and this needs, in addition, a precise alignment of the electronic structure, such, and this I would like to explain here again, that we exactly meet the requirements. What are the requirements? The requirement is that we have a redox potential of 1.23 electron volts for splitting water. This is the free energy we need to provide. Where to get this free energy? This free energy is built up in the semiconductor, and this is shown here by splitting the Fermi levels, by producing the voltage in the semiconductor. So this is the first and most important point in the semiconductor. This means the provision of the chemical potentials of electrons and holes, and this is in the optimum case at a normal illumination of AM 1.5 in the range of 0.4 electron volts, smaller than the band gap. In addition, we need to provide the so-called overpotentials. Overpotentials are needed at the cathodic and the anodic reactions, and in the best case, this is additional 0.1 eV at the cathode, 0.3 eV at the anode, so in addition 0.4 eV. And if we sum up all this, we see to exactly meet the requirements in the optimum case, we need more than 2 electron volts band gap of the semiconductor. This is directed and dependent on the charge carrier concentration on the logarithmic scale, as you can see here. So to look at this again, and at the semiconductor band diagram, we see if we use just one absorber material, one junction, then we can just exploit a small part of the solar spectrum, which you can see here. What do we need to do? We need to create a tandem structure. Since a tandem structure can have both, it can create enough voltage, as you can see here, and in addition, we can exploit the sunlight in the optimum way. So what else do we need? We need now to maximize the current, having exactly the enough voltage here. And this is the next step. This is also educational. Just to mention is the diffusion length of the charge carrier need long enough. It should be larger than, of course, the thickness of the device structure. And in addition, this I already explained, we need to separate electrons and holes in the tunnel junction where we have isoenergetic recombination, and at the electrodes where we also need to separate electrons and holes. Then in the next step, what we need is a high catalytic activity, and this activity we can see here. We need slow overpotentials. This means a good catalytic performance at the one hand, and on the other hand to minimize the interfacial recombination losses. Both challenging and both needs to be aligned electronically and chemically aligned and attached to the device structure. And in the next step, we need high chemical stability, so the passivation or protection of the device structure. Also very important to have this stability and the durability of the device. Having done all this with the device structure on the right-hand side here, it is possible to achieve so far, and we have shown this, solar to hydrogen efficiencies above 19%. If you compare this to the theoretical values which can be achieved, what you can see here is a variation of the different band gaps, and you see here in the bull's eye, you have efficiencies in the bull's eye of around 1 eV band gap and 1.7 eV band gap. And the device structure which we have realized, this is a little off the optimum values. However, it's already a rather good value, which can be improved, but which is already competitive with regard to the solar to hydrogen efficiency. However, there is many challenges still to solve, and the most important is, of course, stability and costs. This I would like to explain next briefly. Costs in the device structure, which I have shown you, are very high. Since this is a piece of art, there's 3.5 on germanium or on gallium arsenide growth. So what do we need to do? We need to bring the costs down. Nowadays, the working horse for these very high performance device structure is germanium, 3.5 on germanium, but as you can see here, with high costs already for the substrates. And this should be brought down by changing this substrate of germanium by silicon. This is some work we already do for quite some time, together with fantastic partners again, Marburg University, Fraunhofer Institute, and others. And this is a major point to bring costs down. Of course, there's much more involved. The epitaxial process itself is very important and needs to be reduced a lot. The silicon substrate themselves, the mass production of the appropriate silicon templates is a strong point, and other topics like the waste management and the waste consumption in basically back end of life and so on. And finally, there might also be a parameter to play with is concentration. Here we need to be careful since we have gases which are developing, so very high concentration needs a lot of bubbles and also change of the optics, so low concentration could be another point to play with. But we have seen in the successful story of solar cell development, photovoltaic growth market, that costs can come down to in orders of magnitude. So this would also be the target which we are also tackling right now together with partners to get this combination of C5 and silicon technology together. I will spend a few more words on this. This in the conjunction of the science behind the challenges which I have already addressed. One thing is, of course, how to look at these very difficult interfaces. One of the difficult interfaces, for example, is the solid-liquid interface. How to look at this, how to control it, and how to characterize and analyze it. For this, the so-called in situ spectroscopy, also operando spectroscopy, are important directions, important fields of science. We are using, for example, this optical in situ spectroscopy here on the left top, called a reflection and anisotropy spectroscopy, which is more or less ellipsometry in normal incidence. Then it is very surface sensitive. It measures the difference of reflection of polarized light with regard to two different crystal axes and gives some difficult signals here. They are not indeed intuitively understandable, but they are highly, they are containing a lot of information, and this is necessary if you, for example, would like to follow the growth occurring in the metal organic vapor phase deposition reactor here down left. And for this, we are using these many methods here. Besides the optical in situ spectroscopy, we are also using benchmarking, surface science, and I will show in the next slide, also using the combination of these methods with photoelectrochemical chamber where we can bring the samples contamination free. This is also very important to look at the surfaces in the electrochemical environment. And this is brand new work we are right now performing so that we can really follow the changes on the surface in situ operando. For example, right top, we can see the change of a well-defined surface, the indium phosphide surface, which is also relevant for photoelectrochemistry. And we see the difference when exposing this surface either to oxygen or to water. And this changes the surface and the surface reconstruction and the surface modifications. So this is all really challenging science, which we are trying to follow with as many expertise as possible. And this means to have very good collaborative work with many different approaches.
Professor, you have 1 minute to conclude.
Yes, I will finish now. Yeah, so it's promising also in this case what recently occurred here by a result of Fraunhofer-ISE showing a new record for 3.5 and silicon direct growth. And this I will jump over just to show you intuitively we already can control fantastic these surfaces and create these necessary double-stepped surfaces on silicon. This is also valuable results for the defect growth of T5 on silicon. So I will finish this talk by just wanting to show that a disruptive method of artificial photosynthesis could lead to the production of clean fuels. It needs a lot of research, and we have been already quite successful. However, there's many things to solve. One is to build demonstrators, which we would like to follow right now in the project. There's a lot of gaps and scientific gaps and knowledge gaps to fill. We need complementary expertise and knowledge, as I already told. And this basically is the challenges finally which we are facing. So finally, I would like to thank you for your attention. Again, thanking the partners and financial support. And yeah, that's it. Thank you.